Welcome to the 10-hour NPTEL online certification course on effective engineering teaching in practice. If you notice, the word teaching is in quotes. That is because teaching is the term that we are all familiar with. It really represents the facilitation of learning by the people who are learning, students, others, and so on and so forth. And that is the reason why the word teaching is in quotes. In this course, we will look at teaching as facilitation of the learning process. My name is GK Suresh Kumar, GK for short. I am in the Department of Biotechnology, IIT Madras. I have an interest in the learning process. I've been doing experiments in the learning process for a very long time, pretty much right from my second or third semester of teaching at IIT Bombay initially. And this particular course will be offered in collaboration with the Teaching Learning Center, TLC for short, at IIT Madras. The TLC faculty who would be involved in about 3 topics out of 12 are Dr. Edamana Prasad, who is actually the head of the Teaching Learning Center, Sripad Karmalkar, Professor Sripad Karmalkar, who is in electrical engineering, who has interests in the learning process, and Dr. Richa Verma, who is with the Teaching Learning Center right now. Teaching engineering needs knowledge and skills on teaching. That is well known. However, engineering teachers, lecturers, or professors have never been trained to teach. Knowledge in that area of teaching is usually considered sufficient to teach that particular subject, and I believe therein lies the difficulty. Merely knowledge is not really sufficient to facilitate learning in others. On the other hand, education is a very old research area. A wealth of information on effective strategies for learning as well as understanding of the learning process is available, which have the backing of evidence. It's not complete, of course, it can never be complete, but a lot of knowledge is available. And most engineering teachers are unaware of the knowledge on learning. It's not in a form that they can access, it is not in a form that can be directly used, and so on. Therefore, this course is also designed to just begin, barely scratch the surface, to begin to address this particular shortcoming or the above 2 shortcomings. One, absolutely no training in the facilitation of learning process, as well as access to knowledge, huge knowledge in this particular area. This is what the course is designed to do. This would be your reference book. You have the cover of the second edition. The title is Teaching Engineering by Philip Wankart and Oriowicz. This was published in 2015. The second edition was published in 2015 by the Purdue University Press. The first edition of this book was published way back in 1993, and that edition is officially available for free download from this particular website. You can go to this website and download the entire book officially. In fact, I happened to began teaching in 1993, the July-December semester of 1993 at IIT Bombay, and I had an opportunity to read this book pretty much from cover to cover just before I took my very first course. I was really hooked on to this book. I learnt a lot from this book, and I'm glad that there is a second edition is available now. And I would use this, or rather we would use this as a reference book. Whatever we are going to do here will not have the same sequence as this or even the same information as this and so on and so forth. But some fundamentals are essentially the same, and we will point it out to you from time to time. The names are all the same, so that should not be a problem. With this, let us begin the first aspect of this course. We will need to begin at a place which is comfortable to most people, and therefore an inexperienced engineering teacher's view, which is what many people are when they begin to teach, because they are essentially not trained. To effectively get this across, I am first going to present 3 scenarios, okay? And I'd like you to watch those scenarios. I'm going to teach mass balance, a useful form of the mass balance. So, I'm sure all engineering people would be able to appreciate it. I've chosen things such that it appeals to all engineering teachers and so on. It's not highly specialized, or none is highly specialized, the examples that have been chosen, and therefore you'll be able to appreciate it. Let us begin with the first scenario. For this, I'm going to go to the board, which is typically available in all classrooms. I will use the board to hopefully demonstrate how various things are. Note, this is a course, or this is a section on material balances. The first scenario is pretty much an inexperienced teacher walking into the class, probably for the first time. So, approach 1, scenario 1, let us begin. Good morning. We are all here to discuss material balance. It's a very important principle that you should all know. Pay attention. You know, if you choose a system like this, and there could be inputs, there could be outputs to the system, and if the rate of input is R in and the rate of output is R out, and the rate of generation is R gen, the rate of consumption is this. Okay, this is very important. You should all remember this. You should memorize this. That is end of approach 1. It might have seemed funny, but you might want to see a video recording of many first time teachers. Now, let us move on to the same thing taught by somebody maybe with a couple of years of experience. The person has realized that there is a class in front, the person needs to facilitate the learning or teach the class, at least facilitation of learning probably comes later, to teach the class, and therefore the person is probably like this. So, right now on to approach 2, a slightly experienced approach. Good morning, class. I am sure you are all bright and sunny, willing to pay attention. Today, we will discuss a very important principle called mass balance. It is a highly important principle, and this is based on the law of conservation of mass. Which is essentially saying that total mass is a constant. Okay, that is the fundamental principle, and we are going to look at a useful form of this particular principle. We will be using this to analyze various different systems, and therefore, let us take a look at this. If we consider a system I am going to represent by this dotted line here. In reality, it could be anything. In reality, it is something that we decide to focus our attention on. It could be this classroom, it could be even as small as this pen, or even a small cell which is a few microns in size, or it could be the entire university, the entire building, the entire universe, whatever you want, entire world, and so on and so forth, whatever you want to call it, whatever we focus our attention on. And there could be inputs, there could be output streams that come out of the system, input streams go into the system, and if we follow the mass of a species could be anything, it could be molecules, it could be compounds, it could be substances, and so on and so forth. We could consider anything as a species. So, there are only a few things that can happen in this context. The species is input into the system at a rate of R n. Okay. So, species is input, it could be input into the system at the rate, time rate, amount per time of R n. Species could be brought out or output from the system at a rate of R out, or this is 1, this is 2, species could be generated in the system. Okay. What I mean by in is this particular space inside the system. Input is from outside to inside, output is from inside to outside. It crosses the system boundaries, input and output, whereas the generation is in the system at a rate of R gen, and species could be consumed in the system at a rate of R consumed or R con. Okay. You think whatever you want, these are the only 4 things that can happen to any species that is being considered over a particular system. The system is very important. Over this system, these are the various things that can happen. Over a different system, over a different volume that we want to focus our attention on, different things could happen. If you look at the net rate, okay, it is quite easy to see by logic that it has to equal the rate in minus the rate out plus the rate of generation minus the rate of consumption. Okay, this is net rate of the species in the system. Okay. The net rate of the species in the system is the rate at which the species gets accumulated in the system. The variation of the mass of the species with time, that when, of course, writing the same thing here, out consumption. This equation, right, can be considered as a useful form of the mass balance equation, of the conservation of mass principle, which can be applied to analyze a system. This is an important principle and you need to know this. Okay. So, that is I think that is all I have here, right. Yeah. that is scenario 2 or approach 2 in this case. Okay. There is one more approach that I would like to show. Okay. What I would like you to do is carefully note the differences between the various approaches. Okay. We will of course discuss that, but I would like you to carefully note the differences between the various approaches. Okay. Now on to approach 3. Okay. Let us begin. Good morning class, I am sure you are all doing well. Okay. Today we are going to talk about a very important principle, especially in the context of analysis, which is the mass balance principle. Okay. And when we talk about mass balance, we will be talking about mass rates. Okay. What is rate? Can you tell me? Right, yeah, rate is amount per time. Okay. And if you have done some engineering course, you would already realize that in engineering we typically talk about rates, rate of this, rate of that, rate of this, and so on and so forth. And it is already a part of you. You may not have even realized that we are talking only about rates. Okay. We rarely talk about amount, volume or mass, volume, and so on and so forth, which we were very comfortable with till the school level. When we made a transition to engineering, we started talking about rates, and that has become a part of you. Why did we actually do that? Would you know? Let me ask you this question. Okay. You have all seen water tankers, especially in Chennai, where we go through water shortages every summer. And these water tankers are the ones that fulfill the water needs for a wide variety of the public. I mean everybody uses water tankers to fulfill their water needs. The water tankers come in various sizes. The small ones are about 8,000 liters, the large ones are about 16,000 liters. Let us choose an average of 12,000 liters. Okay. And I have a figure here, 12,000 liters, and that is a water tanker that I just drew, right. And let us say that we are filling water in the water tanker here. Okay. These go to the filling stations, they get filled with water from a source, and then they come and distribute it to various communities. The volume is 12,000 liters, and this is water. Can somebody tell me what the mass of water in the tank would be when it is full? Yes, right? Yeah, you need the density of water. The density of water happens to be 1 gram per centimeter cubed, or 10 power 3 kilogram per meter cubed, and therefore we are looking at 12,000 liters, right. 12,000 liters. I would like you to work this out. I am not going to tell you how I got this. Work it out. If you have any difficulty in working it out, please get back to me. So, the mass, because of the density being 1 gram per centimeter cubed of 12,000 liters of water, is going to be 12,000 kilogram. Okay. So, now let us ask a question. It is a very valid question, an engineering question. How long would it take to fill the tank, right? All said and done, these water tankers need to go to a filling station to fill up. It is going to take too long a time. It does not really serve the purpose. As short a time as practical as possible would be nice, right. So, how long does it take to fill a tank? This is a very standard engineering question. Can somebody tell me how you would go about it? Yes, you need the rate of filling. Without knowing the rate of filling, you would not be able to find out the time, right. Now, you see the rate coming in, right. So, if you take a look at this, if the input rate happens to be in kilograms per second happens to be 10, you can figure this out. The time it is going to take is 1200 seconds divided by 60, 20 minutes. If the input rate is 20, it is going to take 600 seconds or 10 minutes. If the input rate is 50 kilogram per second, then the time that is taken is 240 seconds or 4 minutes. Okay. So, if you would have done it intuitively, if you think about how you did this, if you know the rate of water input, that is Rn, you know the time is mass per rate, because rate is amount or mass per time, and therefore time is amount by rate, right. So, there you have one direct use of rates, and these are the questions that we will ask in engineering, these that we will be interested in engineering, and therefore we need to work with rates. Let me take this further. Let me tell you, this is simple, you could do it intuitively. There are times when intuition is not immediately available and it becomes difficult, especially in things that you are not very comfortable with. That is a typical rate of 20 kilogram per second. It takes about 10 minutes to fill in a tanker, mid-sized tanker. Therefore, we will choose that rate for further discussion. Okay. Now, let me slightly change whatever we are looking for. Suppose there is a hole in the tanker which oozes water at a rate of 5 kilogram per second. It is filling in at a rate of 20 kilogram per second. It has a hole that oozes water at a rate of 5 kilogram per second. How long would it take to fill the tank? Okay. So, can you work it out? You see, it is not so simple, right, unless it is not so intuitive. You think about it, and then if you see here, you need to look at the net rate. Okay. Once you fix on the net rate, then you will be able to solve this particular problem, this particular question. It is rate of input minus rate of output. Water is getting filled into the tank, water is going out through the hole. Therefore, the net rate is the difference between the two rates, which happens to be 20 is the rate, 20 kilogram per second is the rate at which it comes in, 5 kilogram per second is the rate at which it goes out. Therefore, it is 20 minus 5, 15 kilogram per second. Once you have this, it is straightforward to find out time. The time is mass by net rate, and that will turn out to be 12,000 by 15, which is 800 seconds, or 800 by 60, 13.3 minutes. Okay. So, now you know that intuitively you may not be able to manage it. I will even complicate this further, and then you would be convinced that intuitively you cannot really manage it every time. Now, suppose that in addition to the leak, there is some mechanism inside the tank itself that is generating water at, say, 1 kilogram per second, some reaction maybe, and some reaction in which the water is used up in the tank at 0.25 kilogram per second, and all of which simultaneously occur. Okay, that is the killer thing. The simultaneous occurrence is the one that confuses our intuition a lot. If this is happening, how long would it take to fill the tank? Okay. Now, you know the approach. You need to get at the net rate. The net rate in this case would be rate of input minus rate of output plus rate of generation minus rate of consumption. 20 minus 5 plus 1 kilogram per second is the rate at which it is generated now. 0.25 kilogram per second is the rate at which it is getting consumed by a reaction. You put it all together, it is 15.75 kilogram per second. This is the rate at which water gets accumulated inside the tank, and the rate of change of water mass with time in the tank, which is our system. Okay. And you try to do this with intuition in the beginning, I am sure you would find it difficult. Okay. So, the net rate turns out to be 12,000 by 15.75 to complete that problem. So, that is 761.9 seconds or 12.7 minutes. In other words, rate is a fundamental in terms of usefulness parameter, and you need to start thinking in terms of rates rather than in terms of amounts, say mass or volume that you did in school. Okay. Now, you need to have this firmly set in your mind. Now, let us look at a very important principle based on the law of conservation of mass. The total mass is a constant, and as long as we do not deal with nuclear reaction where there is mass to energy conversion, or we travel at speeds close to that of light when there is mass dilation, we can certainly use this principle. Okay. So, for all terrestrial purposes, it is perfectly fine as long as we do not deal with nuclear reactions. Let us consider a system. Do you know what a system is from thermodynamics and so on? Right? Yeah, right. That is something that we focus our attention on and leave everything out, right? It could be as simple as the classroom here, the building here, or a cell here, a biological cell which is a few microns in size, or it could be as large as a country and so on and so forth. It is something that we want to focus our attention. To this system, there could be inputs, there could be outputs, and these are the input streams to the system, these are the output streams to the system. There are only 4 things that can happen, right? They could if we are focusing on the mass of a particular species, okay. Species could be molecules such as oxygen, nitrogen and so on and so forth. Species could be some complex compounds such as lipids or carbon dioxide and so on and so forth, right. It could be anything that is an inherent or something that can be considered a whole, okay, a whole amount. And if we follow a particular species, then it could be input into the system at a rate of Rn, okay. Everything around the system, if we change the system, everything changes. Therefore, be very careful about the focus of this particular analysis. R input, it could be output from the system at a rate of R out. It could be generated in the system at a rate of R gen. It could be consumed in the system at a rate of R con. These are the only 4 things that can happen, okay. You can think whatever you want. Apart from these 4 things, nothing else can happen to that particular species. Therefore, if you apply the principle of mass, mass cannot be created nor destroyed, okay. Whatever mass exists before the process must, or at the beginning of the process, must be the same at the end of the process. And therefore, if you are looking at the net rate of the species in this particular system, okay, the net rate, it will be the rate at which it comes in, it is coming in, therefore it is coming into the system, minus the rate at which it goes out, plus the rate at which it is being generated in the system itself, minus the rate at which it is getting consumed in the system. Therefore, the net rate of species change in the system is the rate at which the species gets accumulated in the system, which we can represent mathematically as a derivative of the time change of mass, okay, of the change of mass with respect to time, okay. You know the derivative, right? This is not dm dt, you cannot cancel dd out. This is d dt of mass, this is d dt is an operator, you know all this, and this is nothing but rate of input minus rate of output plus rate of generation minus the rate of consumption, okay. In fact, it will be helpful if you just memorize this, it's rather simple to memorize, so that you can directly use it in any situation. You can blindly write this, fit in the various terms, and you would have a very powerful tool for analysis. So that is, I think that's all I have. Yeah. So let me stop here. Okay. First class, I think we are a little over 30 minutes. So that's about the time that you would feel comfortable with. Let's stop here. You think about it. When we come back, we will discuss what were the essential differences between these three approaches. Thank you.